Hello everybody, and welcome to this new Analyst Thursday webinar. I am very glad to welcome you back after the summer break, because today we're going to talk about a very exciting topics, automotive electrification. To do that, I will be joining in a few minutes by Yu Yang, and he will guide you all through the webinar and the different topic of the day. No more waiting. Yu, let's start the webinar.
Thank you, Helen, and hello everyone. This is Yu Yang. And I'm very honored today to be your kind of host of the exciting topic about the vehicle electrification. As indicated from the title of this session, we will really touch upon the hot topics, things like the power electronics, the controllers used in the powertrain side, and also not very important part, the battery. And so I think I'm quite honored today to give you the introduction of the team for this session. And so we'll have a portion from the intelligence from the compound team, and Wilfried from the your system plus on the teardown side of the systems, and also Shalu and from the power team as me, and we also from your intelligence. She will cover about the battery side, and also other colleagues. Amin is also from your system plus, also on the teardown of the power modulators. And the last but not least is Tom, our principal analyst on the MCU, and so also from USS Plus. So I would say we have a really nice mixture today. We have really candidates not only spreading geographically from India, from Europe, from America, and also we are working on different topics. I think today I'm pretty confident we'll bring a very nice overview on the key technologies. So first, let's start from the introduction of electrification. So let's get into the real topics. So talking about electrification, I think everybody knows it's not a really new topic. But here we want to look at it from the other point of view. I think I will just skip all the normal marketing talks. I just want to kind of remind you that where we are with the trend of the electrification. So here at Yole, we adopt approach of so-called the S curve for the innovation adoption. Yeah? So almost all the new technologies, they are adopted in this kind of S curve, starting with something very low in penetration, but then as accumulated that the technology is getting improvement, and to some tipping point, things going to very fast and to end up with the saturation. So this is also help us to understand where we are with the trend of electrification. And as you can see here, that we label with different kind of small icons. So this is for the passenger vehicles. We think is that for passenger vehicles, especially in some leading countries like China, the market is turning to be from regulation driven to market driven. And we are expecting quite fast increase in the adoption in the coming years. And also, on the other hand, I also want to remind you is that passenger vehicle is not the full picture yet. We still have some other vehicle types, things like commercial vehicles. And we see is that they are at quite the beginning of the adoption. So for the, especially for the trucks, they are heavily relying on the incentive, like what happened with the passenger vehicles. So this gives us something kind of 6 to 8 years of gap. So the good thing is that, and for the folks working on the commercial vehicle, they can really learn or benefit a lot from the development for the passenger vehicles. And we will see the whole electrification with basically all the vehicles on the road. So that's our point of view on the total market trend. And then at Yole, I think we are quite specialized also in the market forecast. We will also have a look at what is the market in the coming years. Here we have our focus on the passenger vehicles. Yeah. As you can see here at Yole, we are doing kind of plus 6 years of rolling forecast, and also we go back to the previous years. And here, this is we call it XEV at Yole. It means that all different level of electrification. So starting from the mild hybrid, which is mainly 48-volt technologies, to full hybrid, which is basically you have a complete electric powertrain, but you don't do the plug-in. And then you move a little bit more to the plug-in hybrid, and they have a much bigger battery and also have the capability of getting energy from the electric grid. And then it's the BEV, the battery electric vehicles, which is purely relying on the electrification. And also on top of that, you still have the fuel cell. So as we can see here is that different technologies have really different momentum in the coming years. And overall, we see as the BEV, the BEV has the biggest growth in the coming years till the end of our course, and it will also continue. And on the other side, we also see is that compared to our forecast in last year, we also have some kind of new update. One thing we have changed is that we change a little bit the portion between the plug-in hybrid and the full hybrid because of the quick decrease of the battery cost. And also we extended the lifetime of the mild hybrid because it's not only for the fuel saving purpose, but also it also has the benefit to satisfy the more strict emission regulations. We think for most OEMs, it's not affordable for them to develop a new generation of engine. So the mild hybrid could be an easy way for them to satisfy the emission rules in the coming years before the full electrification. And also we still keep quite low value for the fuel cells. And we think it's for the passenger vehicles, it will be very small volume in the coming years. But things could be different for the commercial vehicles. So this lays out the playground for us, what is the electrification will be. And then this kind of market knowledge in science will check a little bit more on the technical side. So here is a summary of everything we'll be talk about today. So on the BEV, things will be driven by the battery, which is provided the pure energy for a BEV. Things will be driven by the energy stored in the battery, and it goes through the inverters, the OBCs, so all these kind of converters to drive vehicle or have a different load in the vehicle. But also on the other hand, and don't forget is that this is also everything is also controlled by the brain of the vehicle, which is the ECUs, and also is evolving to domain controller, the zone controller. That's also have the impact on the electrification. And also at Yole, as the company specialized in semiconductor, I think we are really the best place to really provide you a detailed analysis on all the key components at semiconductor level or at the component level to understand what's the impact and also what's the support you can get from the key components here. Okay. Talking about the electrification, actually, we know that at Yole, we focus a lot on the semiconductor side, really the enabling the key technologies, supporting the technology trend. And I think nowadays, if you talk about electrification, everybody is pick up the keywords of the wide bandgap materials and things like silicon carbide and also the gallium nitride. And what we want to highlight here is that we think the supply chain of the wide bandgap materials is a very, very attractive one, and also get a lot of people's attention from the tier ones, from the OEMs. So here at Yole, we have a really an expert on the field. Let me introduce Portion, and he will also tell us a little bit more story about the supply chain side of the silicon carbide.
Thanks, Yu, for your introduction. So, hello everyone, my name is Portion Chu. So, I'm a senior analyst in compound semiconductor activity at Yole. So, I'm very happy to have the chance to introduce you and to present you some latest trend regarding silicon carbide and also the global wide bandgap materials to be used in electrification for vehicle. So maybe let's take a look at why we are using wide bandgap. So here I'm referring to silicon carbide, gallium nitride. Of course, as of today, many people talk about the benefit. For example, these materials, they can have like higher conversion efficiency compared with the silicon devices, and also by having the higher power density. So in general, the system, the weight, the size can be reduced. And also compared with the silicon devices, gallium nitride, silicon carbide can also have the operation at higher temperature, which is also very important. As we know, for electrification, for EV. Sometimes it demands also the high temperature operation. But also on the other hand, there's some concerns. For example, as of today, silicon carbide, gallium nitride are more expensive than silicon devices, and also it's also a new technology. For example, silicon carbide, the mass production started around 20 years ago, and gallium nitride started around 2010. So which means this is a new technology compared with silicon devices. So to have this new technology for the system manufacturers, they also have different concerns. For example, is the devices available as of today? And do they have already the reliability by using wide bandgap devices? Or the devices for the wide bandgap can be driven at higher frequency, so which means the gate drivers, the designs will be more complicated, especially, for example, for the E-mode gallium nitride devices. And regarding the higher power density, so which means the silicon carbide, by using silicon carbide devices, you can have smaller die size, but somehow to have the same current rating or to decrease a little bit to have the safe margin. So which are still the kind of concerns as of today by using the new technology of wide bandgap devices. So if we take a look at this one, so what's the position of wide bandgap devices and also the market size? If you split into different voltage rating, for example, gallium nitride, as of today, the 650 volts devices is available, but we are still waiting for the 1200 volt devices to be in the mass production. So which means as we are seeing the EV is moving from 400 volts battery to 800 volt battery, gallium nitride devices is not ready for the moment to support the higher voltage rating. But of course, it can be used. You can use also, for example, the multiple level topology, but which will be more complicated. On the other hand, silicon carbide, it's available for 650 volts and also 1200 volt devices. So which also shows the ecosystem, the supply chain is ready to use silicon carbide for the EV application. So as we can see here, 650 volt devices is already gaining the market size as of today because, for example, Tesla is the main OEM using this kind of silicon carbide devices in their vehicles. But on the other hand, we're also seeing a lot of new trend. For example, the 1200 volt devices for EV, and also by developing the devices at higher voltage, there will be another or more applications in the future for silicon carbide to grow. So let's take a look at the silicon carbide devices, the device market. So as of 2022, we have seen the size of the market. It's around 1.8 billion. And as we can see here, around 70% of the market share is taken by automotive, along with energy and also some industrial applications. And in our most recent and the newly launched report, PowerSeek 2023, we have the forecast to see the silicon carbide will grow to around 9 billion in 2028, with the growth rate, compound annual growth rate at 31%. So the main market driver will still be automotive, and like I mentioned previously, so when the BEV are adapting 800 volts battery systems, you also require higher voltage rating devices. So silicon carbide can also take advantage of the trend. So we can see in 2028, the automotive parts will grow from the market size point of view and also the share point of view. And let's don't forget energy and industrial will also play strong roles to grow the global silicon carbide market. And of course, it's very important to see the supply chain. Do we have any concerns regarding the supply as of today? So this is the overview of the supply chain. As of today, we can see the main IDMs. They have adopted the vertical integrated business model, which means some major OEMs, they have the business activities from silicon carbide through growth, substrates, epi wafer to process, and even to module packaging. So here I'm referring to, for example, the market leader ST Microelectronics and also Wolfspeed, onsemi, and ROHM. Infineon is another major OEM, but they are not adapting the wafer substrates. But of course, you can see here they have activity from epi wafer to the module packaging. So it's still an IDM business model, and in the same time, we can see the major tier one players like Bosch. They enter the silicon carbide business from the device point of view. So as of today, they already have the device manufacturing for the front end and the back end module packaging. So here, this is in general the overview of the business model of silicon carbide today.
Yeah, I think maybe here I want to also make a reminder to our audience is that I think this is a collection of everything on silicon carbide. It's not necessarily for the automotive, I think, but I would say the majority of them will be for the automotive applications. And I think this is a really wonderful work from you, which is widely cited. But for me, it's a little bit, wow, it's kind of a lot of things, information on the same page from the material to the end application. And maybe, Portion, can you give us a little bit of summary on the main trend? What you think is the biggest takeaways from that one?
Yeah, thanks you for the comment and the question. So actually, we can take a look at the next slide. So actually, as of today, in the past 2 years, from 2021 to 22. What has been changed in the supply chain? So if we take a look at the positions of players from the device point of view and also from the silicon carbide wafer point of view. So on the left-hand side, you can see here the top 6 device players. Their market shares has been around between 80% to 90% in 2021, and in 2022 actually it didn't change too much. So the market as of today is taken by the major device manufacturers. So which means the players, they are really supplying to the main application, which will be automotive. And in our understanding, the players will still have a very strong position as they are also expanding their capacity to ensure their leadership in this silicon carbide supply chain. So this is the kind of situation for the device manufacturing. But on the other hand, we have seen some changes of silicon carbide wafer. So the leading players here for wafer supply are Wolfspeed, Coherent, Cycrystal, part of ROHM. But actually, in the past year, we have seen, for example, TankerBlue, this is a wafer supplier from China, and also SKC from CSS, located in the US and Korea. So they have gained significant growth of their revenue in the past year in 2022. And if we look at the top 3 players, they had around 80% of the market share, but in 2022, we can see the market share has been taken by other players. So this is also because of the expansion of capacity, especially for silicon carbide wafers. Many players, they already injected the financial resources to open or to build a new fab. So the capacity will be opened in the coming years. So which means you will also change the ecosystem. More and more players, they are able to supply the silicon carbide wafers. So which will also be a situation for the silicon carbide wafer players to adopt in the coming years. And speaking of the investment and also regarding some merger acquisition, so what happened in the past year? So speaking of M&A, we can see some actions has been done at the equipment level. So for example, ASM acquired LPE for around 425 million euros. And Vico also acquired Epiluvac. So two smaller epitaxial equipment makers has been acquired by the major equipment vendors. So which means the major suppliers of the equipment, they are also looking at the growth of the market, and they implemented some merger acquisition on their side. And also we have seen Navitas, which is a well-known gallium nitride players, acquire Genesic for around 100 million. So this is the M&A happened in the past year. But for partnerships, we have also seen a lot of announcements has been released. For example, Wolfspeed and Renesas announced a partnership and also included the financial deals in this case. And also we have seen some automotive tier ones, for example, Warner, ZF. They signed a long-term agreement with Wolfspeed, but also some investment is included. And the same case for onsemi. So Vitesco and Magna, they signed the long-term agreement. In the same time, they also support with some financial resources to help onsemi to expand the capacity at wafer level and epi wafer level. And also, we are also seeing 8-inch is coming in the future years. So for example, Mitsubishi Electric announced to build a new fab in Japan, but they will need to have the 8-inch wafer supply. So they signed the long-term agreement with Coherent to support their ramp up in the coming years. And Infineon, a very important players in the power electronics, they signed the agreement with Renesas, one of the leading silicon carbide epi wafer suppliers, and also to Foxconn. So Infineon right now, they signed the partnership with the Foxconn in order to supply the silicon carbide devices to this company in the future years. On the other hand, we are seeing, for example, STMicroelectronics. This company is the market leader for silicon carbide devices, and they also want to ensure they can have the ramp up for the next step, which will be the 8-inch. So they signed the partnership with Soitec by qualifying their engineered substrates. On the other hand, the STMicroelectronics also create a joint venture with Sanan Opto in China. So they will have a joint venture fab for the 8-inch manufacturing of silicon carbide devices in the coming years. At the same time, Sanan will also build a new fab for manufacturing the 8-inch wafers for these joint venture companies. So in general, we have seen the market has been very dynamic, a lot of merger acquisition and also partnerships and also co-investment has been announced in the past years. But if you look at coming back to the automotive electrification, and let's take a outlook to 2030. So today in 2023, we have seen silicon carbide entered the many of the electric vehicles. The first case will be Tesla by using the solution of ST in 2017. And today, many companies, for example, the logos you can see here, Wolfspeed, STMicroelectronics, Infineon, onsemi, ROHM, and Bosch, they enter the supply chain of EV. and by seeing the trends to use more 800 volts EV, so the silicon carbide will grow with the trends, especially for the main inverter in the coming years. But on the other hand, of course, we also have onboard charger and the DC-DC. But more or less, it also represents some opportunities for silicon carbide. But it will depend on the pace and the solutions that the OEMs and Tier 1 they will take in the coming years. But in general, the main inverter represents the major opportunity for silicon carbide in the automotive business.
Great. Thank you for the wonderful presentation portion. I think this is a really eye-opener for me, and this also reminded me of, I think, one article you wrote last year. The title is nicely summarized, the clash of the titans, which is really the situation of the major IDMs in the business, I think.
Yes, exactly.
Yeah. Okay. After the really detailed analysis on the silicon carbide part, I think we can go a little bit further from the materials to the devices. As we all know that for power electronics, the substrate material, the device, and also the packaging, they are all very important. So maybe we can start here to look at a little bit more detail about the packaging itself. And also at Yole, we have a pretty unique approach to do this kind of analysis. So now I think maybe we can check the services from the System Plus to see what kind of new information we can get from this analysis.
Thank you. Hello everyone. Thanks for joining. So indeed, I'll talk about power modules from your System Plus side. So my name is Amin Alouche. I'm technology and cost analyst focused on power semiconductors. So just a brief explanation or insight on our methodology at your System Plus. So our core activity is the reverse costing based on process and cost analysis. So after we disassemble a system or a device, we identify its technology and determine its manufacturing process and cost by means of our tools and our models internally. So at your System Plus, we have analyzed different modules. These two modules, for examples of automotive modules, first one from Denso, silicon carbide power module found in fuel cell converter of the Toyota Mirai 2. And on the right, you have the Vitesco power module, the Jaguar I-Pace inverter, which is an IGBT power module. And for both, you see images, package opening, and also package cross sections. So we see, for example, for Denso, an optimized design for dual side cooling for better heat dissipation with top and bottom copper plates. And for Vitesco as well, it uses a quite innovative assembly for die, as you may see, with dual side sintering on the top and on the bottom of the die. And also a base plate structure, which was optimized for direct liquid cooling, as well as its quite innovative silver clip interconnection. So on your System Plus level, we will give, we have analyzed different power modules, different technologies. You can see some of them are based on silicon carbide, others on IGBT. And as you may see, different package types, sometimes customized package solutions. So here indeed we see huge diversity and not really standardization for now. So these power modules have been found in different inverters or converters from different electrification types of vehicles. Here we see battery electric vehicles. Majority of our systems came from this type of vehicle. And also all of them come from fuel cell electric vehicle like Toyota Mirai 2 with both silicon carbide and IGBT based power modules. And you see the full analysis from system, converter, down to the dies we have performed in our reports. and also hybrid electric vehicle. As an example of Toyota Prius 4 with different power modules in its power control unit. So indeed, here we see that packaging really must correspond to the different requirements, both for the application system level and also for the device and the die level as well. That's very important. So if you focus now on battery electric vehicles, here we see a roadmap of the different modules we have analyzed, where we can classify different models of cars, of vehicles, depending on their system voltage, either 400 volt or 800 volt, and also depending on the technology, whether it is silicon IGBT based or silicon carbide based. Indeed, okay, sometimes it's combining, like Hyundai Ioniq 5 combines both IGBT and silicon carbide modules. But in our cases, the trend, indeed, we see more and more vehicles targeting this area with silicon carbide MOSFET modules and 800 volt battery systems.
Okay, great work. And actually, I see really a big variety of the packaging modulars here and there. And yeah, maybe you can give us a little bit of summary from your hands-on experience to tell us what is the main trend you are seeing with the power modular packaging.
Yes, thank you. Indeed, we see different solutions coexisting. It may seem a bit strange at the beginning, but it's the fact that today most OEMs are looking for differentiation from competitors to really achieve a very good balance between performance and cost as well. So different solutions today, from interconnections, which is very important, for example, for silicon to fully benefit from silicon carbide advantages that can go to higher switching frequency, reaching higher power density. So really we're targeting new and innovative concepts of interconnections, going towards lower inductance and also to evacuate heat more effectively. So we can see, for example, the copper ribbons solutions for DAMFOS power modules recently, and also copper clips or optimized spacers with new or more advanced materials than pure copper. Also clips like we saw for Vitesco Technologies power module. Indeed, different solutions today, also for base plates, for substrates, really to target and to tackle different types of challenges for cooling, for conduction, substrate attach as well. So will these solutions or differentiations will perdure in the future? That can be a major point. In our cases, it will be all about finding this winning combination to optimize, again, the performance and the cost and also reliability of the system.
Yes, I think this is really nice. I mean, for me, I think also I want to remind the audience, I think the work at System Plus really set us apart from all the other analyses, because, I mean, the folks, they really have hands-on experience with all the modular devices here. But also you mentioned a very key point by your last sentence, which is the key cost aspect. Can you maybe also give us a little bit more insights on the cost part?
Indeed, cost is very, very important parameter now. So from your System Plus, we have analyzed different power modules. We break down their costs. So here to give you just a brief image without going deeply into details, we analyze different modules. Here notice from A to G, for example. Some of them are based on silicon carbide, as you can see. And what we can notice for silicon carbide, for example, is that the die or silicon carbide die is really a cost driver for the power module, which indeed justifies all the increasing efforts we see now to decrease the cost for silicon carbide dies, to improve the yields, for example, and really to meet the final objective and the cost objective. So Indeed, this cost reduction concept also balanced with the performance reliability is well translated in this right side graph, where we can see that indeed for power modules, while their innovations are improving for performance and reliability, but these factors indeed may increase, as we may think, the cost of the overall module. And sometimes it increases the cost considerably. So many modules on the market today, for example, we see that they can offer comparable, more or less, performances. So if we really think that maximizing the integration of every performance indeed may have its cost impact, and would maybe not be the best approach for module maker to really distinguish and differentiate himself. So especially that cost is a crucial factor for the end customers. And now we're speaking about electric vehicles, so now it will be the electric vehicle users for which cost is quite considerable. So that's why now we may see for module makers moving from rather an excellent power module concept to a good enough and to good enough design approach to really achieve this balance between technical innovation and the final cost of the power module.
So now we move from the device to the system level. So at Yole, you know that we are looking not only the semiconductor devices, but also the electric systems enabling us. And our colleagues from the Sys Plus have really nice work there. So today, and I want to introduce Wilfried, that he will give us some nice examples of how we are doing the reverse engineering on the system level. And now, Wilfried, please.
Thank you, you. And thank you, everybody. I'm very happy to be here with you for this session. So, as you can see, we have a different system that they are very interesting at the system level. Here, I think everybody have in mind this kind of schematics for the electric vehicles. We can see that inside the electric vehicles there are very interesting systems like onboard charger, DC-DC converters, battery management system, power disconnect unit, and also inverters. And it is this kind of system that are very interesting for us to analyze, and that's why we have created since 3 years now a new website that's enabled to our customer to see what is inside this kind of system. This kind of analysis is called reverse costing analysis at System Plus Consulting. We can do it at component level, as we have seen with Amin, of course, previously. But here we have we seen it at the system level. At the system level, for example, we have done almost 40 teardown analysis from different electric cars. The main system that we analyze are inverter, DC-DC converters, onboard chargers, power disconnect unit, and so on. Here it's just some example of what we have done up to date. Every month there is new system that you analyze. And for this session, we would like to focus on a very specific system here, coming from the MG Marvel Air. It's an interesting system because it is called a Combined Charging Unit, CCU, manufactured by Shenzhen Vemax New Energy. It's a Chinese system because we have done a lot of European or American system, and now we are focusing more and more on Chinese system to see what is inside this kind of system. This system is manufactured in China. The weight is 8 kilograms, and when we the first thing that we do when we do the disassembly of this kind of system is to find a lot of information, and the first information that we can find is on the label on the system. And we can see on this label that we have different information about the input, output of the different voltage and currents that are done for this system. We can see that in this system there is an onboard charger associated with a DC-DC converter. It is very interesting to see this kind of mix because according to the previous vehicles that you have seen, sometimes there is only one system for onboard charger, only one system for DC converters, but more and more the tendency is to have an association of different systems, and the objective is to minimize the number of components, the weight of the different electronic system, and to improve the performance also. When we do the teardown analysis, the objective is to do a lot of disassembly steps associated with different pictures, very high level for the quality of the pictures. The objective is to rebuild the bill of material to identify every component on it. Every component, not only as an electronic component for each electronic board, but also all the mechanical parts, all the electromechanical component, and so on. And the objective is to give the maximum of information thanks to the quality of the photo that we done, and also do the most precise and detailed bill of material to be able to cost every component and to have a manufacturing cost of the system at the end of the analysis. By this way, our customer can see all the details without having the system in hand. We can see that on this system there is a lot of electronic board, but we can focus on the main electronic board here. In this electronic board, we can see all the function for the conversion, AC to DC conversion, the boost DC-DC converter. Of course, there is several electronic board, but I focus only on this one. We can see the details of the bottom side also here, with the different microcontroller on it to do the management of all these electrical function. One thing that we have seen here that is interesting is that there is silicon carbide MOSFET transistors here. It is indicated on the different part of the system, and we can see that all the electronic function are done in this board. Conversion AC to DC, conversion high voltage DC to 12 voltage DC also. It is a very compact system. Another thing that we do also, it's we do the block diagram. Here you can see some block diagram of each part for the conversion of AC to DC, the boost conversion also, and the step down conversion. It is very interesting because by this way the designer can see in one view the global functionment of the system here. And here we can see that when we do the bill of material, we do a cost estimation, and we have a lot of breakdown that are also available here. And we can see that the breakdown between the passive component, the discrete, and the processor also. In this system, we have different microcontrollers. There is 4 microcontrollers on this system, mainly 32-byte microcontroller, 2 from Texas Instruments, 1 from NXP, And the last one is 8-bit microcontroller from Microchip here. And we have also done an interesting breakdown because we can see that we have a lot of Chinese Chinese manufacturer, like for the film capacitor with Faratronics, power relay with Angfa, and Olifuse for the fuse. But we have also manufacturer coming from United States and Europe, and we can see that the total breakdown of the material cost is 60% for the Chinese company and 40% for the Europe and American company. So it is an interesting breakdown for this kind of system.
Thank you, Wilfried. I think this is really excellent because for your information, Vmax is really a leading OBC supplier in China. So I think it's opening with this one is really give us a lot of information from China, which is no doubt is also in the upfront of the electrification. And also I want to remind all our audiences that this is just one example. As indicated by Wilfried, we have more than 40 systems. It's up to this kind of level of detail. So check our website. I think we'll put it with the link below. So about the reverse engineering, check the website and do the registration and just have a look at what is available there. Okay, thank you, Wilfried. So let's move back to the next topic. I think so far we have talked a lot about the electronic systems on the powertrain side, but also we see that there are also some other systems also equally important. For example, the MCUs, which is also one of the key enabler of the technology. For example, MCUs, which is one of the key enabler of the electrification technology. So here I want to invite our principal analyst, Tom, to have a little bit of insight on the evolution of the ECUs and what is going on there.
Thank you, for that kind introduction. Today, I'd like to tell you a story about the integration of functions into higher level features in the automobile. Run on microcontroller platforms. Even before the integration of functions into higher level features run in more powerful controllers, the automotive market was approaching a crisis. The demand trend for features was approaching critical mass as the number of electronic control units kept climbing. If something wasn't done, the number of electronic control units would exceed the vehicle's CAN bus limitations, and the weight and the cost of the system would be unmanageable. Two things happened to avoid this crisis. First, the CAN bus has been replaced by lightweight, low-power, high-bandwidth networks such as CAN-FD, which is flexible data rate, and Ethernet networks to enable data to be passed and processed at more centralized locations. Second, with this faster network, more powerful processors, including high-performance multi-core and hybrid MCUs, to consolidate features, eliminating the redundant ECUs and the heavy wiring solutions associated with them. For the microcontroller market, this may have hit the brakes on the unit of MCUs per vehicle, but it has transformed the market for automotive MCUs and even general purpose MCUs sold into automotive to become more proficient at running more and more advanced applications, with the added characteristic of raising the average selling price dramatically for MCUs in automotive. So I'd like to present to you this case, which is actually an acronym for a trend in the automotive world for connectivity, autonomy, sharing, and electrification. This case is a market framework to describe how semiconductors and AI will be critical for the future of automotive. Of the 30 to 80 plus sensors in a modern vehicle, there are an estimated 20 to 50 sensors monitoring an internal combustion engine and associated transmission and fluid systems, with an average of around 30. A fully electric vehicle can get away with fewer because the system is simpler without an internal combustion transmission and fewer fluid systems required. With BHEV or PHEV, the sensors required can go up by as much as 50%. For many of these systems, Automotive certified MCUs are in control of the electronic control units that collect the sensor data. Many of the MCUs for powertrain systems go away with the internal combustion engine, but new microcontrollers are required for power systems for AC charging, charge management, motor, generator, inverter controls, and associated electrical powertrain systems. The trend continues to be to reduce the count of many lower cost, moderate performance MCUs with fewer but higher functioning MCUs with system redundancy and watchdog systems built in. This trend is helping to bolster the revenue for powertrain solutions while the number of overall microcontrollers per powertrain is reduced. The result being a much more functional, feature-rich system with fewer components. But in most cases, the powertrain systems will remain microcontroller-controlled, and the functions will not be combined for upwards in the domain of the vehicle. One of the less obvious impacts of electrification on the microcontroller market is that it has an impact on the consumer's expectations. When a consumer shops for an entry-level or mainstream internal combustion powered vehicle, there are a wide range of options which include budget features like mechanically controlled windows, seat position, mirror adjustments, and similar user experience cockpit applications. With the emerging electric vehicle market, consumers have an expectation that the electric vehicle have electric controls. There are far fewer electric vehicles offering mechanical controls. Likewise, the early adopters of electric vehicles are likely to be well-connected device-wise and will expect the same human-machine interfaces that they've been trained to expect from the rest of the digitally controlled world. This conditioning is driving demand for connectivity and network security that within the domain of microcontrollers to provide. This is not to imply that the instrument cluster or infotainment system, telematics, cabin monitoring cameras, and other video or vision processing are all within the domain of the microcontroller. But the digital controls for comfort, the USB or wireless connectivity, touch interfaces, audio sensors, keyless start, keyless entry, and many other cabin systems are within the domain of the microcontroller. Most of these devices do not necessarily require automotive certified safety. So the number of these systems will come out of your general purpose microcontroller product lines rather than the more expensive, high reliability microcontrollers. Some will be controlled by embedded secure microcontrollers. Ride-sharing is also having a significant social impact and is creating numerous emerging and evolving business models. So it definitely earns its place in the case mnemonic, but in terms of its impact on the microcontroller market is mostly relevant to the heightened use of autonomous vehicle designs targeting ride-sharing. These trends will be talked about extensively further in this presentation, but it's worth mentioning that a significant amount of the autonomous driving breakthroughs are being driven by the ride-hailing sharing market. Further than that, ride-sharing is potentially accelerating the vehicle replacement cycle as operators put significantly more mileage on their personal vehicles. It takes little to no vehicle design changes, but relies on smartphone software and occasionally aftermarket devices. Fleet vehicles are driving an increase in asset management and tracking devices installed, as well as security features. As much as connectivity is adding functions to the cockpit, advanced driver assist systems are pushing modern vehicles into running an excess of 1 million lines of code. As vehicle safety evolves, so too must the entire vehicle architecture in order to support the vast number of new features leading to autonomous vehicles. This illustration provides some guidance on how features continue to become integrated into higher orders of software-defined platforms as we progress through the 6 levels of autonomous driving classifications developed by the Society of Automotive Engineers, or SAE. 2 things to note from this slide, as the protracted use of level 2 autonomy through 2+ and 2++. This is primarily a fault of the standards in overestimating the competency of human behavior to work with the electronic autonomy. Second is the growing dependence on AI as the systems become more complex and dependent upon vision processing systems. This might lead you to assume that microcontrollers will no longer be necessary and that everything will be controlled by massive central processing SoCs with AI acceleration. But this is so far not the entire trend. Microcontrollers continue to play a major role in these systems. To help illustrate the connection between the strategy of advancement toward autonomy and the required hardware improvements, we offer this illustration of the mass market evolution of autonomous driving. It's worth noting that there are already early test beds and limited commuter systems boasting level 3 and 4, but these systems are just emerging and have yet to move the needle on mass market design. Note that the number of sensor systems that are expected for each level of autonomy, while it is a definite trend that the features and functions continue to move away from edge-defined electronic control units toward domain control and zonal control, especially for zones for the pre-processing of vision content and the integration of radar and LiDAR, and final path and motion planning at the domain level. There is still a significant role for the microcontroller at each end of this complex system. At the beginning of this complex system process, sensors such as radar or LiDAR can take advantage of microcontrollers for calibration, data acquisition, and control before passing the pre-processing data up to a zone controller, with more complex application processing typically handled by an SoC. Also, these examples are focused on the primary systems that typically require some intense vision processing to integrate the multiple cameras, and finally, a multiprocessor platform at the domain level to return all of this data into a decision-making function through certain content analysis and path and motion planning. However, what fails to grab the widespread media's attention covering the evolution of this software-defined vehicle is that at the end of this process, the vehicle control is frequently turned back over to a high-reliability microcontroller for control and actuation of the system that actually controls the motion of the vehicle. In many cases, there is an MCU in the domain platform or zone control complexes that enables the system to pass the strict ASIL-D compliance testing required for the safety controlling the vehicle's critical systems in the harsh environments that they must operate. With the growing reliance on video content for advanced driving assistance, there's a big boon in the automotive industry for software development. AI-trained systems, memory capacity to handle the increased data, and SoC platforms to process the millions of lines of code associated with modern vehicles. With this software-defined evolution going on, it would be easy to assume that the microcontroller was being eclipsed. But the demand for microcontrollers as sensor hubs and as system actuator controllers continues. The evolution has also evolved a demand for network security in the form of gateways and secure connected devices, driving demand for secure microcontrollers in automotive. It should also be recognized that for systems that are not processing video content, current premium microcontroller solutions can run deep learning algorithms with modern AI software tools such as TinyML. If the task is to monitor a system to be sure it's operating within safe parameters and alert when maintenance or replacement might be warranted, microcontroller suppliers can target these applications with AI accelerated microcontrollers that are well suited for such applications. So, in conclusion, the market for microcontrollers is not being driven out of the automotive industry by the evolution of the vehicle network, but it's being embraced as a critical and complete system platform within the CASE acronym of connectivity, autonomy, sharing, and electrification. And with that, I'd like to thank you for listening and turn this back over to you.
Thank you, Tom. This is really excellent. I think it's this really provides us a nice overview on the progress with the function of the ECU in the new trend. And also, when we back to our powertrain side, as you indicated, for the powertrain side, the security and also the reliability is a big concern. So for us, the MCU still have a long way to go. That's what my main pickup from here. So last but not least, we come to batteries. Everybody actually knows that the battery is taking something like 40 to 50% of the cost of the modern BEV. So luckily, batteries something like 40 to 50% of the whole cost of BEV. And luckily at Yole, we also have a very strong team on the batteries. So now let's welcome Shalu to give us a nice overview on the battery technologies.
Thank you for the nice introduction. And hello, everyone. I'm very happy to be here. So as you said that now batteries are the most essential part of any electric vehicle. And if you see today's electric vehicles, it's lithium-ion cells are mainly used. And in lithium-ion cells also, we have cells with various chemistries, like in cathode side, we have NMC, it's like nickel, manganese, cobalt oxide, or we have LFP, NCA, nickel, cobalt, aluminum. Anode side, we have graphite anode and silicon-based anodes. So in lithium-ion batteries, we have cells with various chemistries, various formats, and various sizes. Here you can see the lithium-ion battery demands for full electric vehicles. So in 2022, the lithium-ion battery demand for electric vehicle was around 300 gigawatt hour. And by 2024, we are expecting that demand will reach by 1.5 terawatt hour. So now you see that lithium-ion battery demand is growing so fast, or in other words, we can say that lithium-ion batteries for electric vehicle is one of the fastest growing market. Now, if we talk about the technology trends of cells for electric vehicles, we see two main trends. One is electric vehicle cells with high energy density, or the cells with higher performance. So for that, today, NMC, nickel, manganese, cobalt oxide cells are mainly used, and a few players also use NCA chemistries. And if we talk about NMC, then the NMC energy density of these NMC cells are quite high. So today it's reaching around 300 watt-hour per kilograms, and these cells work excellent at lower temperature. So overall performance of these cells are very nice. But then at the same time, if you see the materials used in NMC cells, so it contains few critical materials like nickel and cobalt, especially cobalt. So cobalt, like it's quite expensive, and among all cell components or materials, cobalt is the most expensive material. And it is also associated with some other issues like geopolitical issues, child labors and all. So today, if you see the development area in NMC cells, as like most of the players working on these NMC cells are trying to reduce the cobalt content from NMC chemistry. So like, for example, in the past, we have NMC 111, which had 33.3% of cobalt, but now today we have NMC 811 having 10% of cobalt in NMC chemistry. Then some other players know that they are trying to reduce the cobalt content by adding some other materials. For example, today we have LG Energy Solution, Tesla. They have NMCA, which have a few percent of aluminum and around 5% or less than 5% of cobalt content. The second trend in electric vehicle cells we see is affordability, or the cell with lower cost. So for that, today, most of the players are using LFP cells. That name says that it contains iron and phosphorus. So, but in the beginning, you see that these LFP cells were mainly used by Chinese players, like it was manufactured by Chinese battery makers like CATL, BYD, and used by Chinese electric vehicle makers like BYD, NIO. But if you see that affordability is a global requirement. So today, many players know they already started using or planning to use LFP cells in their electric vehicles. For example, Hyundai is using today, Tesla is using, BYD, Ford is also planning to use LFP cells in their upcoming electric vehicles. When we talk about improvement side of LFP, so most of the players working on these LFP cells are trying to improve the performance. And there are many ways to improve the performance. Like few players, they are adding some other materials in LFP chemistry, like LFPX. For example, we have LFPM containing manganese. Or few players are, like working on this material structure or cell component structures. Or the performance of cells can also be improved by changing the cell design. Like BYD, they have lead batteries, or we have tablet batteries. So different players have different approaches to improve the LFP properties. And today also we see a lot improvement is LFP side. So if you see today LFP cells are, the cost of these cells is quite low compared to NMC. At the same time, they have quite good performance for day-to-day life. So these lithium-ion cells, so in electric vehicle, hundreds of these cells need to be installed to obtain the desired power and performance. So for that, these cells are first connected together to make a battery pack, and this battery pack is installed in the electric vehicle to obtain the desired performance. So in any battery pack, cells is the most essential and important part, but there are many other components also, like we need electrical interconnection, then safety components, and then in battery pack, we have many management system like battery management system, thermal management system to increase the reliability of battery pack. So in electric vehicle, hundreds of cells need to be installed to get the desired performance. And there are many ways to install these cells into a vehicle. The first and the most common way, or the most common approach, we call it modular approach. In modular approach, we have small modules containing few numbers of cells, and these many modules can be integrated together to make a final battery pack. This modular approach is the most common approach, and today most of the players are using this approach. And this approach is actually quite flexible. Flexible means the properties of the battery pack can be changed by changing the number of modules, or same module can be used in more than one car model. So it's quite flexible. But at the same time, you see that that modular pack, when we put modules in a pack, this approach is not so space effective or weight effective, because when those modules are integrated into the pack, a lot of space can be wasted. So for that, we have another approach, and we call it cell to pack approach. In cell to pack approach, cells are directly integrated into the battery pack. So the cell to module step is completely eliminated. So from here, you can see that in cell to pack approach, more number of cells can be integrated into the same size of battery pack. And more number of cells meaning longer driving range and better performance. So today in this cell to pack approach, many players like BYD and BMW, CATL, Tesla, they already started this approach and using this approach in their electric vehicles. And the newest approach is, we call it cell-to-sachet approach, in which cells are directly integrated into the vehicle body. Now, this is the newest approach, and today a few players like Tesla, BYD, and few more players are already, started focusing on this approach. So in general, if we talk about the electric vehicle battery pack improvement area, so we see two main improvement area. One is we need cells with better performance and the cell with lower cost. Today, almost all cell manufacturers are working on these areas, but different players, they have different approaches. But in general, we can we divide these approaches into four main categories. One is material side. So many players, they are focusing on the improvement of material side. Like in anode, we have, initially we had graphite-based anode, but now we have silicon-based anode. So in anode, we have graphite plus silicon. Cathode side, that many that cell manufacturers, they are adding some another materials or more materials into the today's existing chemistry, like we have LMFP, NMCA, and many players, they are working on new chemistries also. The second approach is improving the structure, material structure or component structure, like CATL is doing now for their upcoming cells. And by changing the structure of material and components, performance of these cells can be improved. The third improvement approach is cell design. So cell design meaning many cell makers, they are changing the design of the cell to improve the performance. For example, BYD have longer and thinner cells called braid batteries. Then we have cells with vertical, shape, horizontal shape, tablet cells. So there are various ways to improve the cell design to improve the performance. And last but not the least is a better process and equipment. If we have better process and equipment, in that case, the cell manufacturing yield or cell component manufacturing yield can be improved. And once we have a better yield or lower losses, it will directly impact on the cell cost. So if we have better yield, the cell cost of the cell would go down. So you see there are various ways to improve the performance of cells or to reduce the cost of the cells, and different players have different ways to do that. Yeah, thank you.
Well, this is really nice because I really like it. It's provide you a really good structure to see where the innovations will come from. And so actually talking about batteries, we are moving the topics from electronics to chemistry. So maybe for the batteries, there will be also a different supply chain. And also I see actually in previous pages, seems the OEMs are also getting more vertically integrated. Is it also the same case for the battery?
So maybe I can show you something about supply chain, how this electric vehicle battery pack supply chain is revolving. Here you can see electric vehicle battery pack supply chain. And in this electric vehicle battery pack, there are many components starting from raw materials to we have cells, modules, packs, and different other components like thermal management system, battery management system, housing, safety components, and many more. So first, let's talk about the most essential part of any battery pack is cell. So today, if you see that this cell manufacturing is mainly dominated by Asian players. Now, we have CATL, BYD, then we have LG Energy Solution, Panasonic, Samsung, and many more. But then today you see that many European players and American players, they also started making electric vehicle cells. And when we see these cell manufacturers, they are actually vertically integrated, meaning apart from making cells, they make their own battery modules and battery pack. At the same time, as you said, these car makers are also getting integrated or interested in total electric vehicle battery pack. And most of the car makers like Nissan, Volkswagen, Ford, Tesla, BMW, and many more, today they make their own battery modules and battery pack, meaning they buy cells from cell manufacturers and different components, and then they make their own battery modules and battery pack. So you see that this supply chain is quite vertically integrated. So one player can make more than one component. Similarly, in case of battery management system also, today many cell makers and car makers are also interested and making their own battery management system. But at the same time, if you see that other components like thermal management system, housing, safety component, and part of BMS, there are many pure players are involved. Meaning these players, they only involve in one type of component, especially like you see that thermal management system. So the players are pure players. They only focus on thermal management system, or the players involved in housing are focusing only on housing. So overall, if you see that this electric vehicle battery pack supply chain is very interesting, and we have seen in the previous slides that market is also growing very fast. So in general, I would say that this electric vehicle battery pack market is quite dynamic, and many players of different expertise, like hardware experts or software experts, can get opportunity in this battery pack market.
Wow, this is excellent. I think it's a really nice overview on the supply chain side of the battery. And as indicated, it's highly dynamic. So I would suggest the audience stay with us to see what is the things coming on the horizon. So this is the last talk today. I hope everyone has enjoyed kind of the nutshell of the key technologies for electrification. So just allow me to quickly wrap up what we have learned today. And the first things I would say is that electrification is really a step trend. And also it's not only for the passenger vehicles, actually it's with all the segments and also happening everywhere in the world. So with that context, we see actually all the key semiconductor components we are focusing on, plus batteries, they are really the enabling technologies for the electrification. So stay with us to really learn the state of the art in the innovation. I think is very important. And also, as we have discussed in several sectors, supply chain is reshuffling because there's already new things coming up with the industry, and there's new suppliers coming up, especially in the case of batteries. And also we see is that the OEMs and also tier one, they are getting more and more vertically integrated. So that also brings a lot of new business and changing the horizon of business. And the last but not least, I think we have shown in the different talks, I think we have really uniquely positioned to really have a nice expertise in different key aspects in the revolution. So I think we are really a good partner for you, for everybody in the whole supply chain to really go through this revolution of the industry and stay in the front of the innovation. And so this is basically end up the talk on all the excellent the contents of today. But just one reminder is that my colleague Ellen will also give you a few introduction of all these works comes from some of the information so far for reports and also the other products. So stay tuned. Yeah.
Thank you, Yu. Indeed, we have several products related to the topic that you can see on your screen right now, such as report, monitors, and teardown. You can also benefit from our current special offer on our website to get directly the product. So now the webinar is ending. So we'd like to thank you for your attendance. Thank you, Yu. Thank you to the speakers of today. I hope you enjoyed a lot the webinar. You will find the replay and the presentation on our website from tomorrow. Let me remind you that the next webinar will discuss about smartphone with a special focus on imaging and display. You can register right now on our website. I'd like to thank you all again and see you next time.